Thank you. Thank you everyone for coming to this talk. So first I'll begin by thanking the organizers. So I requested that I give this talk online because I live with someone who is immunocompromised, and I was initially not sure how many would be in the auditorium, but I sense the auditorium is not all that packed, so maybe I could have just come in person. But anyway, thanks to the organizers. And I also want to give a caveat that since this is a very short talk, I'm skipping a lot of attributions and references. Ask me later if you're interested. So I'm going to start with something very elementary. I'm going to give you a problem in linear algebra. You could explain this problem to an interested undergraduate student who has just finished a course in linear algebra. And if you want to make the student, spend some time working on some fun problem, this is a problem you could give them. And the problem is the following. So think of the following matrix equation in three matrices, M1, M2, and M3. I asked that these matrices obey equation 1, which is that their product should be the identity matrix. I'm taking these matrices to live in the general linear group, which is basically the group of n by n invertible matrices with complex entries. I'm always going to consider matrices with complex entries today. So what we would like to understand is all possible solutions to equation 1. So this is a very basic question in linear algebra. To give you a kind of different read on this, so let's just assume all of these matrices are semi-simple, and hence you can diagonalize them. So let me write this equation in a slightly asymmetric form. I'll push one of these matrices to the right-hand side, and I'll write this as M1, M2 should be equal to M3 inverse. So from this, you can see that the kind of question we are asking is, if you know the eigenvalues of M1 and M2, and you multiply the two of them, what are going to be the eigenvalues of their product M1 and M2? This is a very common kind of question that arises in linear algebra and so on. But you can also think of sort of analogs of this question where you don't work with objects in the group, but you say work with the corresponding Lie algebra. In that case, equation 1 would be replaced by a similar statement where you have sums of matrices that live in the Lie algebra, and you would ask that they sum to the identity there. So there's a similar problem where you replace GLN by the group of unitary matrices or its corresponding Lie algebra. In that setting, this kind of question is called the Horn problem. It's again a very classic problem. It was solved in the 90s by Kleatschko, Knudsen, and Tau. So what I'm talking about today kind of belongs in a similar orbit of ideas. So one important thing to immediately notice is the moment you have one solution, it's easy to generate new solutions. You just pick some arbitrary element of GLN. You conjugate each of these matrices, call them, M1 prime, M2 prime, M3 prime. You just attach PP inverse on both sides. You can see that this also gives a new solution. So the interesting question really is to ask for solutions up to conjugacy. So in other words, what are the conditions on conjugacy classes, say Ci, living in GLN, such that there exist representatives Mi belonging to these conjugacy classes Ci, solving equation 1 that I wrote on the previous slide. Now, it's also natural to ask for one additional condition on these solutions. And this condition is going to be that I ask the matrices Mi, viewed as linear operators on Cn, I ask that they don't have a common invariant subspace. Such solutions are called irreducible. Now, the reason we ask for this is, so imagine the opposite is true. They have a common invariant subspace. What that kind of tells you is that secretly, they are somehow a solution for a smaller value of capital N. And that's somehow showing up as a reducible solution for a higher value of capital N. Those are fine. You might want to study them. But somehow the sort of truly new things that arise at some value of N are these irreducible guys. So it makes sense to mark them as a separate category, and that's what I consider today. Okay, so that's the problem. So if you're giving this to an undergraduate student, you should probably do them the service of restricting the problem to some low values of N. So let's say you ask the student to work out the case for N equal to 2. So your matrices are going to have some eigenvalues, 2 of them for each of the 3 matrices. Clearly, they should obey the condition that the determinant of M1 times determinant of M2 should be determinant of M3. This is going to be some condition on these eigenvalues. Now, it turns out this is the only condition you need to impose. As long as this is obeyed, you can always find solutions to the equations I wrote. There are no further interesting conditions on these conjugacy classes, mainly because there aren't many interesting conjugacy classes in GL2. But even in this case, there's a non-obvious fact. It turns out all solutions to equation 1 are actually conjugate to each other. In other words, up to conjugacy, the moduli space of solutions is actually a point in this case. This is a non-obvious fact, which you could ask the undergraduate student to check. Mathematically, this moduli space being a point is something known as the property of rigidity. Okay, so now let's go to the next case, which is n equal to 3. Here we have something more interesting. We again have the determinant condition, obviously, but we additionally have the following conditions on the multiplicities of eigenvalues. So for example, if the multiplicities of the eigenvalues of the 3 matrices were just 1 cube, 1 cube, 1 cube, which is to say they all have distinct eigenvalues, a non-trivial moduli space of solutions exists in this case. And if you make one of the matrices have repeated eigenvalues, in that case, you can still find a solution, but this is kind of similar to the GL2 case that I outlined earlier. In this case, you have a unique solution after conjugacy. In other words, you have some, again, phenomenon of rigidity. Funnily, for any other choice of multiplicities, there is actually no irreducible solution. So for small n, what I just outlined to you, the results, they actually go back more than 100 years, at least to Riemann's study of local solutions to the hypergeometric differential equation. So the solutions are written in terms of what are called Gauss hypergeometric functions. So if you've played with them in some course on ODEs or something, there's a complicated story of how they transform under monodromies and so on. So Riemann sort of studied this problem, and he was secretly using the fact that their corresponding local system, as it were, had this rigidity property that I was talking about. So it turns out a direct attack on this problem for some higher n is pretty hard. In fact, I don't know of a direct way to solve this problem. All known solutions sort of go through some highly indirect approaches. But before I tell you about those approaches, I want to give you a generalization of this problem to more matrices. And that is basically what is called the Deligne-Simpson problem. So basically, you ask for necessary and sufficient conditions on conjugacy classes Ci, which for simplicity, I'll take them to live in SLN instead of GLN, such that there exist representatives Mi in these conjugacy classes that obey this matrix equation that says the product of all of them should be the identity matrix. There's an interesting and nice geometric interpretation of this problem. So it turns out this is equivalent to asking for the non-emptiness of what is known as the irreducible character variety, in this case of a P1 minus P plus 1 points. So I'll tell you what this definition means. This is basically defined to be the moduli space of irreducible representations of the pi1, which is the fundamental group of some algebraic surface. In this case, it's the P plus 1 punctured Riemann sphere into SLN. So to specify a representation like this, what you would do, for example, is think of the independent generators of this fundamental group. They're going to consist of loops around each of the punctures. And you want to specify the image of this map for each of those loops. They're going to be matrices like these. But so these generators are not all independent. They actually obey one relation, and that relation is exactly this equation 3 here. This problem in linear algebra that I was talking about has this extremely interesting geometric interpretation. For some historical reasons, this moduli space is also called the moduli space of local systems. And this is an important object in topology, algebraic geometry, and number theory. So I've been talking about the moduli space. There's also something called the moduli stack, and you can also work over arbitrary fields and so on. So if you're an algebraic geometer, all of these would be very natural things to do. So it turns out this moduli space.
I think you have 5 minutes.
Yeah, is best thought of as a part of a triplet of moduli spaces. One being the moduli space of local systems, another being something called the moduli space of flat connections, and the other being something called the moduli space of Higgs bundles. So I'll sort of skip the details, but the punchline here is that there's a way to go between each of them. And I'm particularly interested in the first column here, which is the moduli space of Higgs bundles. So what Simpson did in 1992, which is pretty recent considering the history of this problem, is he used this non-abelian Hodge setup, which is the sort of columns I showed you on the previous slide, and he gave a solution to a particular case of this Deligne-Simpson problem. He assumed that one of the conjugacy classes is regular, and in this particular case, he wrote out some necessary and sufficient conditions. I'm not going to explain them to you, but they exist, and this was known in the literature. So far, this has been some story about a pure math problem. What is the connection to quantum field theory? In particular, I had the word superconformal field theory in the title. So it turns out there's a class of 3D n equal to 4 superconformal field theories related to these moduli spaces of Higgs bundles. In particular, the Coulomb branch of these theories is this Higgs moduli space, or which is also called the Hitchin moduli space. So given this, it's natural to wonder if the solution to the Deligne-Simpson problem is related in some nice way to some properties of these quantum field theories. Now, independently, motivated by some physics questions having to do with monopole operators and so on, Gayato and Witten had proposed a kind of trichotomy for all 3D n equal to 4 theories, without any relation to Higgs bundles or anything like that, a classification for all 3D n equal to 4 theories, and they call them good, ugly, and bad theories. It turns out for today's talk, it's good to just combine the good and ugly cases and give them a common name. We'll just call them okay. So you just have a dichotomy between the ones that are okay or bad. So in some work that I did with Ron Donaghy and Jacques Dissler, so we had to translate what this okay condition meant in precise mathematical terms to the language of Higgs bundles on smooth curves. We needed this as a preliminary first step to set up the problem of studying the Hitchin integrable systems on nodal curves, which are singular curves. So, I mean, that's the main problem we were studying, and the paper is mainly about that. But one of the surprising things that we found as a consequence of having to do this groundwork is that in these regular cases that I mentioned, that Simpson studied, asking for the corresponding Higgs bundle to be okay in this sense that we defined, turns out to be same as asking for Simpson's conditions to hold for the local system, which is the thing on the third column that I showed you. So this was surprising to us. So we then went and played around with more examples, relaxed this condition that one of the conjugacy classes has to be regular. And we always found that this is true. So this gave us confidence to make a bold conjecture that at least in the strong form of the conjecture, it says the okay condition is always necessary and sufficient for the existence of a solution to the Deligne-Simpson problem. So this gives a different perspective on a lot of existing math results. There's a huge bunch of technology that's been used to attack this problem over the last 2-3 decades. For example, there's something called Katz's middle convolution algorithm. There's work of Prole-Beauvais and collaborators using quiver representation theory and so on. So all of these things have a natural sort of way of appearing in this 3D n equal to 4 setup. In other words, if somebody who's only interested in 3D n equal to 4 theories, you just hand them this family of theories, they would have somehow discovered all of this for themselves without knowing any of the math literature. So we are currently in the process of writing up a paper to sort of explain these elements of this dictionary. You can also use this identification to physics to try and understand a similar question for other groups. So you can perfectly well pose the question for any Lie group, not just GLN. In particular, you can ask this question for groups like Dn, which is the group of SO2n, because there the connection to physics is a little clearer. So here, a lot of this math technology is actually absent or not completely worked out. But interestingly, physics has some hints to give, but these remain to be translated to math and checked. So this is something that we are currently working on. I've also been talking to Pranav and his students about connections between everything I told you today and some questions in hyperkähler geometry. So a lot of these moduli spaces that arise, they are naturally hyperkähler, and it's interesting to ask what happens to the hyperkähler metric under some natural operations in the story. And this is also, the fourth point here is also something I'm extremely interested in. So the Deligne-Simpson problem should also be intimately connected to questions in Liouville and Toda. Yeah, I'm done here, basically. Yeah. Liouville and Toda conformal field theories. And the corresponding bootstrap problem. But this is actually surprisingly poorly understood. And I'm happy to chat about that with anyone who's interested. So yeah, thank you. I'm done.
Thank you, Aswin, for your talk. We can have at max one question.
Hello, can you hear me?
Yes, yeah. Hi.
Just a small question. So can you say maybe briefly, what is this OK condition from the point of view of the gauge theory?
It says that the R charges of the monopole operators should be at least 1. I might be off by a factor of 2, but it's a statement about R charges of monopole operators in 3D n equal to 4 3s.
Okay, thanks.
Okay.
Sorry, just I was curious how it would be connected to the Liouville and Toda. If there's a very quick answer, you can tell me. Otherwise, I can chat with you later.
Okay, yeah, there's not a quick answer. So, but roughly speaking, so say for an arbitrary Toda conformal correlation function, we don't know exact answer. There are special cases where there's an extension of the DOZZ work, like Fatih, Lichunov, and so on. They have explicit answers, right? Now, every case where you have an explicit answer is sort of secretly connected to something like a rigid local system. Now, more generally, more arbitrary local systems should be related to the more complicated correlation functions. And so this whole question of whether there is an irreducible local system or not, corresponding to the correlation function is extremely interesting. And the answers in this local system language should have some interpretation in CFT terms as well. I don't think this is known.
Okay, so let's move on, and let's thank again Aswin for his talk.